Hello, welcome to lecture number 4. So this is continuation of the discussion on holography. So recall we were discussing the expression for the formation of the hologram. So let me quickly recall a few details. We have the reference beam which is given by this expression, right, which is R is the amplitude and is exponential I omega t plus phi. This phi is the phase, which is a linear variation of the phase across the film. So it's a uniform illumination because R is uniform and the phase of the beam varies linearly across the film. Now if you look at the signal beam, which is the object beam that is coming, I'm writing this E signal, and it has got an amplitude variation which again is a function of x and y, the two coordinates corresponding to the film, the surface of the film, and s is a function of that's amplitude. And you also, of course, it's at the same frequency as the reference, but then there is also a phase which might be spatially varying, which is what is captured in this theta xy. So if I simply take the intensity of the signal beam, I would get essentially these phase factor will be cancelled out, and what we would get is basically a map of the amplitude, and that's what is captured like so, and this is what is captured in a 2D photograph. So what we are doing in actually a hologram is to add both these, the reference beam as well as the signal beam, add it up, and then record that intensity arising out of these amplitudes in this manner, right? So I'll just come to the last expression, which is what we had derived in the last class. So you get an expression which is so. Okay. Now a few things to recall. Remember that R is a uniform intensity. S has got a structure which has got x and y dependence. Phi is a uniform linear phase variation, whereas theta has got a structure which is xy dependent. Absolutely similarly, the theta and phi here in the complex conjugate part. Now, when you are looking at the transmittance through the hologram, so what I talked about until now is the recording process. So when you look at the reconstruction process, what you record is basically the transmittance on the film, which is proportional to the total intensity as specified above. For reconstruction, what you do is you again put in the reference beam that goes through the transmittance, which is governed by the earlier total intensity. The holographic field which you generate is coming out of the reference being scattered off from the film with that transmittance. So here are the essentially three terms. You can clearly see that r square plus s square, which is the 0th order, right? It is, so what you have is the reference beam whose amplitude is now changed a little bit. Okay, so it has got a spatial variation which is exactly like the original reference beam, no change. There is an amplitude variation which is that. So this is the beam that goes through without any diffraction. It is along the direction of the original reference beam. Now let's look at the second term, right? This second term has got a uniform intensity r square, which you don't worry about because r square is uniform across the whole beam. And then it has got exactly the form of that of the signal beam. You have S, which indeed is a function of x and y, plus you have got this theta, which again is a function of x and y. So you see that there is no other space-time dependence in this part. So what you get is the signal which was emitted by the original object. It is simply multiplied by a r square term, which is a uniform illumination, right? So that's the only difference that you have in terms of the original beam. So let us look at this third term, which is interesting. So you have got r square, which again is the uniform illumination, which you don't worry about. You have got again the same amplitude s, but there is an exponential I omega t. And you see that strangely now the phase has got a reversed sign, right? It is it is no longer plus theta, but it's minus theta. So you see that what was, for example, lagging of the phase has now become the other way around. It has become the phase has come ahead, and the phase that was ahead is now lagging. So you see that the phase is inverted in this last term. Not just that, there is another multiplying factor which is exponential I25. So you see that this exponential I25 is actually at an angle 2 alpha, because phi was an angle alpha. So now you see that this new beam has got not only the reversed phase, it has got the right amplitude, of course. So you get a similar object. It has got the reverse phase. The phase is inside out, if you like. And its orientation also is not the original orientation. It is oriented at an angle 2 alpha from the original beam, right? So that is the, so this is that, so this part, the third expression, is the real image that is formed, which is what is the upside down reversed slightly uh, weird looking image. But the correct image that we are interested, which is what is this virtual image. So this virtual image is the original light as though it is scattered from the original object. So now let us just look at a few properties of this hologram, just to emphasize a few aspects. I've written it down. So you see that even a small portion of the hologram basically contains with it nearly the whole information, right? Of course, it is not the whole information. So a small portion will contain that perspective of the object. Okay, so different small parts are going to contain essentially the whole perspective from that viewing angle. Of course, the perspective, the kind of image you would see from a small piece has a degraded resolution arising purely out of the fact that the aperture has been reduced, right? So that is one aspect. The other important thing is that the image has got both depth and parallax. That is something very important to keep in mind. That was the original purpose of having this hologram. Um, Now you can be creative, and you can actually arrange things such a way that one includes multiple exposures, right? That is, I can have the same film, but I can have, for example, reference beams coming at different angles, containing, for example, different colors. So you see, I would be able to create now on the same film. I'll be record multiple amount of information, probably with just varying uh, the angles of the reference beams. So if I now come in with a reference beam at different angles, I'll be able to project out like a hologram different information which is recorded at those particular angles. So you see that the amount of information that can be packed inside a hologram uh, can be quite immense. All right. So now let us look at different types of holograms. Okay, I just discussed a few types. Okay, most importantly, I want to get to something called the volume hologram. But let's just deal with it one by one. So so the first type which I want to discuss is the rainbow hologram. So what you do in the rainbow hologram? So let's first understand. If I change the reference beam. So for example, my reference original was omega 1. This was my recording original. And I now, for reconstruction, I use omega 2, which is not same as omega 1. Then you know what happens is basically the image changes. The image is looking, of course, like the new color. But there are distortions that happen. The distortions is that the angle at which you see this new uh, image will be different. Not just that, there will be some sort of a magnification which I will talk about later. That will magnification either magnification or demagnification, that depending on the relationship between omega 1 and omega 2, you will see that kind of scaling that happens. Okay, so now the other thing I can do is I can expose this hologram to multiple frequencies together, like a white light. Then what happens? So when you see that if you put in white light, the colors get mixed up, because you see, from as the white light is coming at the same angle, at different angles, different colors are getting scattered, and these will get all basically mixed up. So rainbow hologram does something neat. What it does is that you restrict the horizontal view while recording. So for example, you will record a series of horizontal strips, which might be RGB, for example, colors, red, blue, and green, and so on. So what would happen is that if I now view this hologram in white light, you'll see that different colors are going to be seen at different angles. So as you view this hologram, okay, you will see different colors in the vertical direction, whereas so in vertical direction there will be no parallax. You will only get you only get different colors, whereas the depth and parallax business will be there in the horizontal direction, right? So that is what is called as a rainbow hologram. So the second hologram which I want to discuss about is the embossed hologram. So these are basically used consumer items. It gives you a sense of authenticity that is made by the company and so on. So it's used as a anti-counterfeiting signature of the company. So what one does there is basically records the hologram on a photoresist, okay, and then applies, develops it there, so you form grooves, right? And then what you do is then you deposit a thin layer, for example, of nickel or some metal like that, nickel layer deposition, right? Once you have deposited that, you peel off. So now you see that the peel off contains basically the replica of the grooves, but inside the metallic film, in a sense. Now that is called a shim, and this shim is now used to emboss. Now this is used to emboss the with a roller under high pressure and temperature. Basically, you can produce mass production of these embossed holograms. Lots of consumer products which are used for used as a mark of originality by the company. So the third type of hologram which I want to discuss is the volume hologram. So here what you have is you have a film thickness which is large compared to the fringe spacing, right? So you have a medium in which you are going to record in the volume of the medium the fringes, right? So recall that the fringe spacing, which largely depend on the wavelength. So you have now got fringe spacing, you've got a thickness of the film which is larger than that. So for example, you can come in with the E reference from one side, and you can come in with the E signal from the other side, right? And in this volume now, you are basically going to record fringes, which is the overlap of these two, and you're recording that. And so if you recall, these, so what you're going to form is basically in depth, you're going to form layers of high and low contrast, because depending on the change in the refractive index is going to depend on the intensity of the interference pattern that is generated within this. So just imagine that these were uniform beams. You will just basically record a parallel set of fringes, right? With alternating bright and dark, right? So that is a kind of that's a kind of recording that you're going to make in this thick film. And you know that this, in such a thick film, you would now quickly recall that now when I come in with the reference light, the light is going to be scattered across this volume. And quickly you will recall the Bragg's law. Remember, in the Bragg's law, you have these layers, and you're coming with light, and these light, and this is the reference light essentially, which is getting scattered in some direction, right? And of course, the scattered light basically forms. So that's my normal. So this is my angle, let's say theta, with respect to the surfaces. So you see that, and if the spacing between these high and low, between the two high refractive index layers is d, then you see that I get a scattered maxima if my path length corresponds to d sine theta, that is my 2d sine theta, when it becomes a integer multiple of lambda, right? So you recall this Bragg's law. So now what happens is, uh, in the volume hologram, you see that in a particular direction, a specific lambda gets scattered. So a single lambda gets reinforced at a particular theta. So the thicker the film or the emulsion, you see that greater is going to be this reinforcement of a particular lambda in a particular direction. So what I can do here now is I can actually create multiple exposures with three primary beams, right? So for example, I come in with E reference uh, and E signal both in the red. I can come in with the blue. I can come in with the green, and they are done at three different times. You have three different recordings, so you have now multiple exposure by three primary colors, and now you can actually produce. So when you put in white light, all of these wavelengths get reinforced in the same direction. Hence, you produce basically a 3D image in full color. Now, there are a variety of applications, by the way. So I'll just quickly go through some. I'm certainly not, I cannot be exhaustive. So among the applications, I want to maybe talk about a few. So the first thing I want to talk about is non-destructive testing. You superimpose the virtual image, the expected virtual image, onto the object itself, right? And then you see that the slight changes that are there would actually will be clearly seen as fringes or distortions. Okay, so that is one way of doing non-destructive testing. So the second thing is the time-averaged holographic interferometry, wherein what you study is basically vibrating surfaces. So imagine that the object is continuously moving during your recording, during the exposure time. What you are able to now discriminate is actually the modes of vibration, because you see they are going to be, so when you have a vibration, there are going to be nodes and antinodes across the surfaces which are generated. The nodes are not going to move, whereas antinodes are going to move. So as they move and you are averaging over this variety of cycles, you will see that you get a blurring where the antinodes are formed, and you will get very clear images where nodes are formed. So you see that one can basically analyze, study this vibrating surface by using this time averaged holographic interferometry. The next important application which I want to talk about is microscopy. In microscopy, what you have is, this is the magnification that you get. Wherein the magnification is given by these ratios, where Q is going to be the distance of the hologram to the image, whereas P is the distance of the object to the um, to the film. So you see the magnification is given by these ratios. So typically this ratio can be 1, for example. But now you see you can come up with this business of, you can play around with the wavelength of recording and the wavelength of reconstruction. So the imagine that the hologram is made when it's recorded, it is made, for example, in X-rays. It is being viewed, reconstructed, for example, with visible light. So, for example, the X-ray wavelengths of order of about 0.01 nanometers all the way to tens of nanometers. So you can see that there is a 2 order of magnitudes there and another, and you have in the visible, so X-ray recording, visible light, you are reconstructing, you can easily get about 10 to the power of 4 magnification or so. So you see the small structures which you will be able to record would be clearly magnified and seen. And it is basically these ideas that that led to that were extremely promising, that led to the Nobel Prize for Dennis Gabor. All right, the other next application which I want is basically data storage. Now we can clearly see that a volume hologram, imagine the volume hologram, it can be reoriented and new exposures can be recorded on it. You can have a variety of multiple exposures. So this small rotations, for example, would be equivalent to turning pages of a book, where every page is recorded at a particular orientation, and the reliability of the data recorded is extremely high, because you see the data is not localized and stored at a particular location. It is actually, the data is recorded across throughout the hologram, throughout the volume of the hologram. So you see that it becomes a very becomes a very powerful tool to, even from a damaged a finite locally damaged volume hologram, one can still retrieve the complete data. And at the very end, I want to talk about holographic optical elements. Okay, so these are basically flat lenses, mirrors, prisms, and whatnot. So you can basically record the light coming out of these onto flat surfaces of holograms, because they create essentially the same diffraction pattern as one would get arising out of these particular elements. So one can actually create extremely light plastic based, transparent plastic based holograms which are flat, which can be put inside very small devices. These are, by the way, used as heads-up display in aircrafts, where you have the various meters which the pilot is looking at, that is projected onto his windshield, so that he has a complete clear view of the instrument as well as the of the space outside. So one is able to basically create these flat optical elements which can be inserted to get very complex functions. So particularly, I think high resolution gratings are actually replacing the conventional gratings which are made of this holographic optical elements. All right, thank you very much.